Hi everyone. In this video we're going to talk about what's called the logistic growth model. Previously we discussed a model of population growth in which the growth rate is proportional to the size of the population. So you probably remember that as dy over dt equals ky. With this model, the population grows exponentially, because if we solve this differential equation using separation of variables, it ends up equaling y equals c e to the kt. Okay, so we've already learned about this model in the past. The problem with this model, though, is that in many situations it's unrealistic, because in this model your population would keep growing exponentially forever. But that's often not possible, because at some point the environment cannot sustain that population growth anymore. Okay, so in many situations this model is unrealistic because environments impose limitations to population growth. For instance, you know, if it's, let's just say, a population of rabbits, you know, eventually the rabbit population is going to get so big that they're going to start running out of food, water. They might have disease start spreading throughout the population. So, you know, the environment can only sustain the population so long. So a better or more accurate model for population growth is often what we call the logistic differential equation. And it looks like this. dp over dt equals k times p times 1 minus p divided by L. I was just trying to circle the equation. Okay, so in this model, P is the population, well, dP over dt is the rate at which the population is changing over time. K is still the growth rate of the population. But what's new in this model is L. L is the maximum population that can be sustained or supported as time increases. A population that satisfies the differential equation does not grow without bound as in exponential growth, but approaches L, which is called the carrying capacity, as time increases. Okay, so again, L is the maximum population that can be sustained or supported by the environment. Okay, now we can solve this differential equation by separating the variables and then using the partial fraction technique to integrate. So let's do that. Okay, so remember, our differential equation is dP over dt equals k times p times 1 minus p divided by L. Okay, so the first thing I'm going to do is separate the variables. So remember, I want P and dP on one side, and then I'm going to keep K and dt on the other side. Okay, so after a little bit of manipulating, we end up with 1 over P times 1 minus P divided by L. dP equals K dt. Okay, so notice I have my variables separated. So the next step would be to integrate both sides. Now, integrating the right side is easy, because that's just going to equal kt plus c. But integrating the left side is going to take a little bit of work. But again, we're going to use partial fractions to integrate the left side. So, in order to use partial fractions, I am going to rewrite the left side as L divided by P times L minus P. Now, where did that come from? That comes from just multiplying top and bottom by L. and then distributing L in the denominator. Okay, but now I could use separation, I could use partial fractions. So I would end up with A over P plus B over L minus P equals L over P times L minus P. Okay, so now for me to solve for A and B, I'm going to end up with A times L minus P plus B times P equals L. Now keep in mind, you guys, that L is a constant in this equation. Okay, so remember, to solve for A and B, we pick convenient values. And the convenient values are for P. Okay, so for instance, let's just say we set P equal to 0. If I set P equal to 0, I'll end up with A times L equals L. And then if I solve for A, L divided by L equals 1. Okay, my next convenient value, I'm going to let P equal L. So if I do that, I end up with L times B equals L, divide by L, and I get B equals 1. Okay, so we end up integrating 1 over P plus 1 over L minus P dP on the left side. And remember, that just equals K dt, which we're also going to integrate on the right side. Okay, so now we can integrate. All right, so on the left side, we'll end up with natural log of the absolute value of P plus natural log of the absolute value of L minus P equals K times T plus C. Okay, now, on the left side, there is one more thing that I need to do when I integrate. When I integrate the 1 over L minus P, it's going to be natural log of the absolute value of L minus P, but then divided by -1, which is the derivative of L minus P. So actually, this ends up being a negative. Okay, so now what I'm going to do is I'm going to condense the left side into a single logarithm. And because I'm subtracting my logarithms, this will condense into division. All right, and remember, we're trying to solve for P here. So the next thing I would do is exponentiate each side. And so I'll end up with P divided by L minus P equals C times e to the kt. All right, now, in order to solve for P, I would next multiply by the L minus P on both sides. And then next I'm going to divide by the C e to the kt on both sides. Okay, so that gives me P over C e to the kt equals L minus P. And then, remember, I'm trying to solve for P, so I'm going to add P. We're going to get there eventually. You're probably thinking, what the heck? But I'm going to add P to the left side. So I'll have P over C e to the kt plus P equals L. And then what I'm going to do is I'm going to factor out P. So that'll leave me with 1 over C e to the kt plus 1 equals L. Okay, now, instead of keeping this 1 over, I'm going to use my properties of exponents, and I'm going to flip that. and make it C e to the negative kt plus 1 equals L. And then I'll just divide on both sides, and we finally get P equals L divided by, and often you'll see it written like this, 1 plus C times E to the negative KT power. Okay, so this is the equation that you get when you solve the logistic differential equation, and this is what's called a logistic growth model. Okay, now keep in mind that L is still your carrying capacity, K is still your growth rate, T is still time, and then of course P is your population. Okay, now what does that graph look like? Well, this is what the graph looks like, and it's sometimes called a logistic curve. And so you can see that we have time along the x-axis and then our population size along the y-axis. And so early growth is modeled by an exponential function. Okay, so this graph kind of starts out, or the population starts out growing exponentially, which is represented in red, but eventually the growth begins to slow and then taper off. And so you can see that happening in blue. And eventually it's going to reach that carrying capacity, which is a horizontal asymptote. Okay, so a couple things that you want to be familiar with. Well, you want to know what the basic shape of a logistic curve is, because sometimes you'll be asked to, pick a graph represented by the differential equation or the solution to the differential equation. The other thing is, a couple parts to this graph that are important is that horizontal asymptote, okay, because that's your carrying capacity. So one of the things you want to be able to do in these problems is determine the limit of the population over a long period of time. This is always the carrying capacity, and it's regardless of the initial population. Okay, so what we're saying here is that the limit as t approaches infinity of P of t equals that carrying capacity, or is equal to L. Okay. All right, the next thing you want to be able to do, so we're talking about the fact that the graph is approaching that HA. Okay, the next thing you want to be able to do is determine the limit of the rate of change of the population over a long period of time. Okay, so now we're not talking about the population, but we're talking about the limit as t approaches infinity of the rate of change of the population. So that's dp over dt. Okay, so what do you notice? We're talking about basically the slope when you look at this graph. So hopefully you're noticing again, as t approaches infinity, because this graph is leveling off and becoming more horizontal, and slope of a horizontal line is 0, that this limit would be equal to 0, or the rate of change of the population is approaching 0 over a long period of time. Okay, the third thing, you want to be able to determine when the population is growing the fastest. So the population is always growing the fastest at the point of inflection. Okay, now hopefully you are noticing that this graph is concave up and then concave down. So there's an inflection point right here. And the inflection point represents, I can scroll down, when the population is growing the fastest. And it's always when the population is half of the maximum carrying capacity. So again, if we go back to the graph, you can notice that's probably, it's usually about halfway. Okay, this is L up here. And so this would be 1/2 times L. Okay, so here we would say that P, the population is growing the fastest at 1/2 times L. Okay, so you guys, those are 3 important things to recognize. Well, recognize what the graph looks like, but then also know that the limit of the population as t approaches infinity equals the carrying capacity, and the limit as t approaches infinity of the rate of change of the population is 0, and that the population is always growing the fastest when the population is half of the carrying capacity. All right, so let's look at some examples of the type of questions you might be asked. Okay, so in some of the multiple choice, you'll be asked to match a graph to the logistic differential equation. So here, our equation is dy over dt equals y times 10 minus y divided by 60. Okay, so hopefully you'll recognize this right off the bat as logistic growth, or if we solved this differential equation, it would result in a logistic growth model. So if you know what that basic shape is, you could eliminate A and B right off the bat. Okay, because we know we're looking for a logistic growth graph. Okay, so C and D both look like they could represent logistic growth. The main difference between graph C and graph D would be the horizontal asymptote, which would represent the carrying capacity. Okay, because for this graph, it looks like the HA is at 600, and for this graph, it looks like the HA is at 400. So let's go back to the equation. How can we determine the carrying capacity from this equation? Well, remember that the rate of the population over time is approaching 0. So that can only happen when either y equals 0 or when 10 minus y divided by 60 equals 0. Because you guys, if you notice, this equation is in factored form. So, you know, if we were setting our equation equal to 0, because we know dy over dt is approaching 0 as t approaches infinity, then we would get this equation, and then we would set each factor equal to 0. Well, when y equals 0, you know, that's this point here. That's really not what we're interested in right now. That would be like your initial population. We want to know when 10 minus y over 60 equals 0. So, because that would represent our carrying capacity. Okay, so if I solve this equation, if I subtract 10 on both sides, I get this, and then I can divide by -1 on both sides, and then I can multiply by 60, and I get y equals 600. So 600 is our carrying capacity, and so at that point we could eliminate D, and we know that C is the correct graph. Okay, let's look at this example. The number n of t, or the number of trucks represented by n of t, of a certain model that were sold within t months satisfies the logistic differential equation. There were initially 20 million trucks sold. What is the limit as t approaches infinity of n of t? Well, again, we know that this limit is equal to the carrying capacity. So we're actually going to do exactly what we did in number 1. We know the carrying capacity is going to come from setting this factor equal to 0. So we have 90,000 minus 3 times n divided by 20,000 equals 0. We will subtract 90,000 on each side. And then we will divide by -1 on each side. Then we will multiply by the 20,000. Okay, so we're going to get 2 times 9 is 18. And then I'm going to need 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Whew. Oops, I put my comma in the wrong place. There we go. All right, then we're going to divide by 3. Okay, so we're going to end up with n equals, well, 18 divided by 3 is 6. And then again, I'm going to need my 8 zeros again. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's count every 3. So n equals 600 million. And that would be our carrying capacity, which would also be the answer to the limit. Okay, one last example. This time, n of t represents the number of people who have adopted a certain fashion style after t months. And we've got our logistic differential equation, and then it says initially there were 3,000 people who had adopted the style. But the question we want to answer is, what is the number of people who have adopted the style when it's growing the fastest? Okay, so again, we have to find the carrying capacity because we know that the number of people who have adopted the style when it's growing the fastest is going to be 1/2 of the carrying capacity. So again, to find our carrying capacity, we're going to set this factor equal to 0. And solve for n. And then we'll just find half of it. Okay, so again, I'm going to subtract 1/10 on each side. And then we'll divide by -1 to get rid of those negatives. And then we're going to multiply by the 1,800,000 on both sides. So we'll get n equals and then that is our carrying capacity, 180,000. You guys, all I did is just move my decimal one place to the left, or basically you just drop a 0. If you're multiplying 1/10 times the 1,800,000, then you just end up dropping a 0. And now we're at 180,000. Okay, but this is our carrying capacity. So we know that the number of people when the rate is growing the fastest is half of that. And so half of 180,000 is 90,000. And that would be our final answer. But hopefully you're recognizing that we are basically using these 3 important pieces of information. Okay. All right, so you guys will definitely practice some more questions in class. As always, thank you for watching and have a good night.